Welcome to Section 2 of Chapter 22, Organic Chemistry. This section will have two videos dedicated to it, and in this one we will talk about saturated hydrocarbons. Alright, so as always we'll go through key terms and main ideas as we go through the lesson. So we'll just begin. Hydrocarbons are compounds that contain only carbon and hydrogen. They make up the simplest class of organic compounds. All other organic compounds can be viewed as hydrocarbons in which one or more hydrogen atoms have been replaced by other atoms or groups of atoms. So hydrocarbons are the simplest class of organic compounds is what we need to know as for now. And they tend to consist of solely carbon and hydrogen. Hydrocarbons are grouped mainly by the type of bonding between carbon atoms. Saturated hydrocarbons are hydrocarbons in which each carbon atom in the molecule forms 4 single covalent bonds with other atoms. Single covalent bonds, as we talked about in the previous video, means 4 sigma bonds. Yep, so our first main idea is that alkanes contain only single bonds. So alkanes are a subgroup of hydrocarbons. Hydrocarbons that contain only single bonds are alkanes. In figure 2.1, the molecular formulas, structural formulas, and space-filling models are given for alkanes with 1 to 4 carbon atoms. If you examine the molecular formulas for successive alkanes in figure 2.1, you will see a clear pattern. So we'll look at it a little later. Each member of the series differs from the preceding one by 1 carbon atom and 2 hydrogen atoms. For example, propane, its molecular formula is C3H8, differs from ethane, C2H6, by 1 carbon atom and 2 hydrogen atoms, a CH2 group. This CH2 group is also known as a methylene group. So then we have ethane and propane, their structural formulas. Here is ethane. As we see, propane has 3 carbon atoms, and we also see that in the molecular formula, and so the only difference between the two is 1 carbon atom and 2 hydrogen atoms. So compounds that differ in this fashion belong to a homologous series. A homologous series is one in which adjacent members differ by a constant unit. So they differ by a constant unit, okay? It is not necessary to remember the molecular formulas for all members of a homologous series. Instead, there's a general molecular formula that can be used to determine the formulas, just like in math. So when we look at the molecular formulas for ethane and propane, C2H6 and C3H8, they both fit the general formula CnH2n plus 2. So this is a general formula for alkanes. For ethane, N equals 2. So there are 2 carbon atoms, and then plugging in 2 for N here, we get 2 times 2 plus 2 equals 6 hydrogen atoms. For propane, N equals 3. So there are 3 carbon atoms, so N is 3, so it's C3. And then we plug in 3 for 2, we get 2 times 3 plus 2, 8 hydrogen atoms. Now, consider a molecule for which we do not know the molecular formula. Suppose a member of this series has 30 carbon atoms in its molecules. Then N equals 30, and there are 2 times 30 plus 2, 62 hydrogen atoms. The formula is C30H62. Incidentally, an alkane with this formula, known as squalene, does exist and is a component in some moisturizers. Now, I've written here that this is a general formula for alkanes, and I would like to do a quick recap of what makes an alkane an alkane. So you can identify an alkane if it consists of only carbon and hydrogen atoms, And then the bonds between all molecules have to be sigma bonds or single bonds that we can see from their structural formulas. If the bond between all atoms is just a line, then we know it's a sigma bond. And then a third factor is that the molecular formula has to be of the form CnH2n plus 2. So you can just look at the molecular formula and tell if it fits this general formula for alkanes. Now let's have a look at figure 2.1 as we were asked to do. Here we see the molecular formulas and then structural formulas and the three-dimensional models. So CH4 is methane, and here we can see its structure. All four hydrogen atoms circle the single carbon atom. Then we have ethane. It's similar, but another methylene group is added in the middle. That's and it reflects the general formula, right? And then as we add another carbon atom, we have 3 carbon atoms now, and then we add 2 hydrogen atoms, and we get this. And similarly, here as we add another carbon atom, we add 2 more hydrogen atoms. And now we'll go back to isomers, because as we see in this case, there are 2 possible ways to arrange all the atoms. That gives us 2 different molecules. So notice that for alkanes with 3 or fewer carbon atoms, only 1 molecular structure is possible. So if it's 3 or fewer carbon atoms, there's only 1 type, right? Like 1 structure possible. However, in alkanes with more than 3 carbon atoms, the chains can be straight or branched, which is why alkanes with 4 or more carbon atoms have structural isomers. And if you notice, they are structural, butane and 2-methylpropane, because they do look different right away. When we look at them, they look different. It's not just that the location of atoms is rearranged in space, but they have a different structure. They're branched. So yeah, molecules that have more than 3 carbon atoms, they can have a straight or a branched structure, as we see in this case as well. So butane has a straight chain of atoms, and 2-methylpropane has a branched structure, because we have 3 carbon atoms, and then the 4th carbon atom is branching from the main hydrocarbon. So the number of structural isomers increases greatly as the number of carbon atoms in alkanes increases. So isomers are directly proportional to the number of isomers is directly proportional to the number of carbon atoms in alkanes. For example, there are 3 isomeric C5H12 alkanes, 5 isomeric C6H14 alkanes, and 9 isomeric C7H16 alkanes. And as we get to C25H52, there are nearly 37 million possible isomers. However, most isomers have never been prepared or isolated, probably because we don't need so much of them. Now, I would give you the chemical names for these compounds, but as we already talked, they have many isomers, and each of those isomers has a separate nomenclature. That is why, like, a general chemical name for this compound would be pentane. For this one, it would be hexane, and then for this one, it would be heptane. Do you see the pattern? 5 pentane, 6 hexane, and 7 heptane. We'll get to that in a second, because the naming of organic compounds has a very structural format. But yeah, all of them have many isomers, and each of them have different names. Our second main idea is that cycloalkanes have a ringed structure. So cycloalkanes are alkanes in which the carbon atoms are arranged in a ring or cyclic structure. So as the name implies, cyclo means like a circle. The structural formulas for cycloalkanes are often drawn in a simplified form, using skeletal representations. They call it skeletal representations because they look like skeletons, right? So here's an example of one, and it is understood that there is a carbon atom at each corner, and enough hydrogen atoms to complete the 4 bonds to each carbon atom. So we know for sure that at each corner there's 1 carbon atom, but there's a carbon atom at each corner and enough hydrogen atoms to complete the 4 bonds. So we don't know how many hydrogen atoms there are at each corner, and we'll have to identify it for ourselves in each individual case. For example, in this case, there are 2 hydrogen atoms at each corner because that's how many hydrogen atoms we need to complete the 4 bonds to each carbon atom. So the general structure for cycloalkanes, CnH2n, shows that they have 2 times n hydrogen atoms, 2 fewer hydrogen atoms than non-cyclic alkanes, CnH2n plus 2 have. In other words, in cycloalkanes, there are twice as many hydrogens as there are carbon atoms. So this is something we need to know. This is because cycloalkanes have no free ends to which additional hydrogens have to be attached. Another example of a 4-carbon alkane and cycloalkane is shown below. So here we have butane and cyclobutane, and we see that cyclobutane has 2 less hydrogens because it doesn't have these free, so-called free ends, where the additional 2 hydrogens can attach themselves to. So as we got acquainted with a skeletal representation already, cyclobutane can also be drawn as a simple square. So at every corner there's a carbon atom, right? So carbon, 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 and then we just need 4 bonds for each carbon for its outermost shell to be full. So here we have, for example, this carbon, it has its 4 bonds, so it's happy. So does this carbon, 2, 3, 4. And then this carbon will also have 4 bonds, as well as this one. So that's how we can determine the number of hydrogen atoms that need to be attached. Or sometimes there will be a double bond, but that's not for hydrocarbons. Yeah, so that's how we can draw cyclobutane simply as a square. Now let's answer our check for understanding question. So it asks, even though they don't follow the general formula CnH2n plus 2, why are cycloalkanes still alkanes? So think about it for a second. The answer is that cycloalkanes are still alkanes because they consist of only single bonds. As you might recall, that is one of the factors that we wrote out. So if a hydrocarbon consists of only single bonds, we can consider it an alkane. Yes, so cycloalkanes are still alkanes. Next to our third main idea. Organic compounds have systematic names. This part of the section is very interesting because I personally love anything that has a structure to it. So historically, the names of many organic compounds were derived from the sources in which they were found. As more organic compounds were discovered, a systematic naming method became necessary. The systematic method used primarily in this book was developed by the International Union of Pure and Applied Chemistry, abbreviated IUPAC. Unbranched chain alkane
nomenclature. So we're gonna talk about unbranched chain alkane nomenclature and branched chain alkane nomenclature. So unbranched chain means that the compound is simply a chain. It's in a straight line. So we're talking about straight lines here. To name an unbranched alkane, find the prefix in figure 2.2 that corresponds to the number of carbon atoms in the chain of the hydrocarbon. Then add the suffix "ane" to the prefix. So it's "ane" because it's alkane. So we're just using this prefix everywhere when we want to refer to alkenes. An example is shown below. So the molecule has a chain 7 carbon atoms long. There's 7 carbons in this chain. So the prefix "hept" is added to the suffix "ane" to form heptane. Here we have figure 2.2. And we see that we're naming unbranched chain alkanes based on the number of carbon atoms. So not hydrogen atoms, not any other kinds of atoms, but carbon atoms. And then, as you might recognize, these prefixes, they look familiar, don't they, from geometry or just like simply naming polygons. So these are familiar to us. But the first 4, they're a little different. So meth for 1, eth for 2, prop for 3, and but for 4. Yeah, so we just add the suffix to the corresponding number of carbon atoms. Now we'll talk about branched chain alkanes and how to refer to them. So the naming of branched chain alkanes also follows a systematic method. The hydrocarbon branches of alkanes are alkyl groups. So here we have our next key term, alkyl groups. They are groups of atoms that are formed when one hydrogen atom is removed from an alkane molecule. So now we're looking at a hydrogen atom being removed. Alkyl groups are named by replacing the suffix "ane" of the parent alkene with the suffix "il." Some examples of alkyl groups are shown in figure 2.3. Alkyl group names are used when naming branched chain alkanes. We will present only the method for naming simple branched chain alkanes with only straight chain alkyl groups. Consider the following molecule. So before we'll consider the following molecule, I want to bring your attention to the suffixes. When we're referring to alkanes, so alkanes, we have the ending "ane. And the suffix that we use for it is "ane," unsurprisingly. And when we're dealing with alkyl groups, it ends with "il," and that's exactly the suffix that we're using for the to name the compound. Yep. Now we can consider the following molecule. We see a lot of hydrocarbons. So to name this molecule, we have to locate the parent hydrocarbon. The parent hydrocarbon is the longest continuous chain that contains the most straight chain branches. In this molecule, there are 2 chains that are 8 carbon atoms long. The parent hydrocarbon is the chain that contains the most straight chain branches. Do not be tricked by the way the molecule is drawn. The longest chain may be shown bent. Okay, so we are looking for a chain that contains the largest number of straight branches. So that is the parent hydrocarbon. It's nice that they have pictures here. It's easier to explain. So the parent hydrocarbon in this compound would be this. So the one in red and pink. This would be the parent hydrocarbon because it has, let's count how many branches. It has 1, 2, 3, and 4. But we might be tricked by the fact that it has a straight chain, right? That kind of looks like a parent one, but it has only 3 branches going from it. That is why it's not the parent hydrocarbon, and this is. The first one is, because it has 4. So to name the parent hydrocarbon, add the suffix "ane" to the prefix "oct" for a carbon atom chain with 8 carbon atoms to form octane. Now identify and name the alkyl groups. So we located the parent hydrocarbon. It's this one over here. And since there are 8 carbon atoms in this parent hydrocarbon, it's an octane. Okay, so we're now talking about the alkyl groups, the branches, and they're highlighted in pink here. There are 4 of them. The 3 CH3 groups are methyl groups. So we have another name. This is methyl. It's called methyl, a methyl group. So the CH2 and CH3 group is an ethyl group. Yay, another name. Ethyl group. This one is also known as C2H5. So we now arrange the names of all alkyl groups in alphabetical order. And we put them in front of the parent hydrocarbon name. So E comes before M. That's why it's ethyl methyloctane. And this first parent hydrocarbon name will always be at the end. To show that there are 3 methyl groups present, we attach the prefix tri to the name methyl to form trimethyl. So now it's not ethyl methyloctane, but it's ethyl trimethyloctane. And now we need to show the locations of the alkyl groups on the parent hydrocarbon, because we need to identify where these alkyl groups can be found. Number the octane chain so that the alkyl groups have the lowest numbers possible. Now this is getting interesting. We have to number them this way and not this way because this way the first methyl group has it falls under the number 2. Then the ethyl groups is 3, and then the other 2 methyl groups are 4 and 5. If we were to number them from here to here, the first 2 methyl groups would have the numbers 4 and 5, which is the opposite of what we need. So now we have to place the location number of each of the alkyl groups in front of its name. Separate the numbers from the names of the alkyl groups with hyphens, and the ethyl group is on carbon 3. So we see that the ethyl group is on the third hydrocarbon, so that's why it's 3-ethyl trimethyloctane. And because there are 3 methyl groups, there will be 3 numbers separated by commas in front of trimethyl. So each alkyl group will have its own number to represent its placement in the so from where does it branch off of the parent hydrocarbon. So we see that the methyl groups are under the numbers 2, 4, and 5. That's why the full name is now 3-ethyl 2,4,5 trimethyloctane. The procedure for naming simple branched chain alkenes, similar to this one, can be summarized as shown in the list on the next page. But before we look at that list, let's read this part here. It's quite interesting. Careers in chemistry, and how petroleum engineers can apply what we just learned in real life. Petroleum engineers search for underground reservoirs of oil or natural gas. They then work with other scientists and engineers to develop and oversee drilling and production operations. Petroleum engineers are also responsible for developing technology and methods to increase the amount of oil or gas obtained and to lower the cost of drilling and production operations. In addition to possessing a broad range of engineering expertise, chemical, mechanical, or electrical, a petroleum engineer must also apply the basic sciences of chemistry, geology, physics, and mathematics. So this is applicable because oil and gas are 2 major sources of hydrocarbons, and hydrocarbons specifically. So, yeah. Now let's look at the alkane nomenclature that we just used to find the name for this compound. Now this can be used generally only when we're dealing with simple branched chained alkanes. So they're simple branched chain alkanes. First, we have to name the parent hydrocarbon, like we did in the example above, and that parent hydrocarbon will be the longest continuous chain of carbon atoms that have straight line branches, that have the largest number of straight line branches. Then we add the suffix "ane" to the prefix corresponding to the number of carbon atoms in the chain. Next, we will add the names of the alkyl groups. We'll have to identify those alkyl groups first, and that is why it's important to know, for example, that a CH3 group is a methyl group, and that a CH2 attached to a CH3 is an ethyl group. So that's why it's important to know like these names. So add the names of the alkyl groups in front of the name of the parent hydrocarbon in alphabetical order. So again, this is important. When there is more than one branch of the same alkyl group present, attach the appropriate numerical prefix to the name. Di for 2, tri for 3, tetra for 4, and so on. You can refer back to that figure that we looked at. So do so after the names have been put in alphabetical order. Yeah, that's kind of obvious, because if we were to add prefixes to the names first, the order might change, because, I don't know, like D comes before tri, even though E comes before M. So we have to put these, these in alphabetical order before we add the prefixes. The third step is to number the carbon atoms in the parent hydrocarbon. If one or more alkyl groups are present, number the carbon atoms in the continuous chain to give the lowest numbers possible in the name. If there are two equivalent lowest positions with two different alkyl groups, give the lowest number to the alkyl group that comes first in the name. This will be the alkyl group that is first in alphabetical order before any prefixes are attached. So I'll have an example here. So let's consider this imaginary compound. First, we would identify the parent hydrocarbon, right? It would be the same one as here. I tried to use a similar one just for the sake of explaining. But we are running into a little problem here, because if we want to arrange, if we want to number the parent hydrocarbon in a way that will have the alkyl groups with the lowest numbers possible, we can't do that here, because no matter how we number the parent hydrocarbon, it stays the same. So the numbers will be 2, 3, 6, and 7. And if we were to do it in the opposite direction, it would still be the same. 7, 8, 2, and 3. Oopsie. Yeah, 2 and 3. That is why, when there's such an occasion, if there are two equivalent lowest positions with two different alkyl groups, give the lowest number to the alkyl group that comes first in the name. So then we would look at the name. It would be, up to this point, it would be ethyl methyloctane before any prefixes are added. Here, before any prefixes are added, this is to emphasize. Ethyl comes first. So ethyl is found here, and that's why we want to give ethyl the lowest number possible, and not any other alkyl group, not methyl in this case. So that is why we would number the parent hydrocarbon this way: 2, 3, 4, 5, 6, 7, and 8. 3. It has the lowest number. Our fourth step is to insert position numbers. So we would put the position numbers of each alkyl group in front of the name of that alkyl group. 5. Punctuate the name. Use hyphens to separate the position numbers from the names, and if there is more than one number in front of the name, we use commas to separate the numbers. So yeah, this just summarizes what we did above. And now there's some more practice problems. First, there's an example. Name the following simple branched chain alkane. So the alkane we see has the longest continuous chain that contains 6 carbon atoms. That is why the parent hydrocarbon is hexane, hex standing for 6. Second, we identify and name the alkyl groups attached to the chain. We have 3 branches here, 1, 2, and 3. And there's only one type of alkyl group with 1 carbon atom, so they're all methyl groups. Alkyl groups with 1 carbon atom are methyl groups, so we add the name methyl in front of the name of the continuous chain. It would be methylhexane, and then when we add the prefix tri to show that there are 3 methyl groups present, it becomes trimethylhexane. The third step is when we number the carbon atoms in the continuous chain so that the alkyl groups have the lowest numbers possible. So yeah, here we see that the alkyl groups have numbers 2, 3, and 5, and not 2, 4, and 5, as it would be if we were to number them in the opposite direction. Then fourth step and final step, the methyl groups are on the carbon atoms numbered 2, 3, and 5, so we put the numbers of the positions of the alkyl group separated by commas in front of the name of the alkyl group. And we separate the numbers from the name with a hyphen. So numbers are separated from the name with a hyphen, and the numbers are separated from themselves with commas. Now we have 2 practice problems to solve on our own. Feel free to pause the video and try them using that table with rules and steps for naming simple branched alkene compounds, and come back when you're ready. So when we consider this first hydrocarbon, it's quite obvious that the parent hydrocarbon here is this long chain of hydrocarbons, because it's the only possible option that would have the longest number of carbons. So 1, 2, 3, 4. And from figure 2.2, we know that 4 stands for but, so, and then the ending would be ane, so butane. Then following our steps, we will identify all alkyl groups. Here we have only one alkyl group, and it's CH3 or methyl. Since there's nothing to put in alphabetical order, it will be the only one in front of butane, so it's methylbutane. And now we number our parent hydrocarbon so that this branch can have the lowest number possible. So it will be 1, 2, 3, 4. The methyl group will have the number 2. So our final answer is 2-methylbutane. Now, the second one. This is an interesting one because I would like to get your attention on one interesting thing. So, again, when we're first looking at the compound, we can say easily that this is the parent hydrocarbon because it has the largest number of chains, right? 2. Okay, and let's first go in this direction. It has 6 carbons, which means that we'll have, and it's an alkane, so it will be a hexane. Hexane is the name of our parent hydrocarbon. Now we're considering our alkyl groups, our branches, CH3 and CH2 attached to a CH3. So this one is a methyl group. So a methyl group, and then this is an ethyl group, just like in the previous example. Ethyl E comes before M in the alphabet, so it will be ethyl methylhexane. And now just like always, we number our parent hydrocarbon. Now, this is the case where we have to look at the name that comes before. The name that comes before to understand like which way do we have to number the parent hydrocarbon. So we don't have to add any prefixes here because there's only one methyl group and one ethyl group, and ethyl comes before, so we need the ethyl group to have the lowest number possible and not the methyl group. So it will be 1, 2, 3, 4, 5, 6, and not the other way around, because again, ethyl comes first. That's why it should have the lowest number possible. And then we just add these two numbers in front of their names. So 3 ethyl, and then we'll have another dash, and another dash on the other side of the 4 because the this methyl group falls under the number 4. So yeah, sorry, it's a little dirty, but yeah, 3 ethyl 4 methylhexane is the final name. And now what I want to show you is the other way we could come to the same answer. So as I said, the most obvious parent hydrocarbon here is the straight line, but there's also this part that has the same number of carbon atoms. 1, 2, 3, 4, 5, 6. So it's 6 carbons again, and it still has these 2 branches. So in this case, it wouldn't matter which parent hydrocarbon we would pick because everything would stay exactly the same. We would look at we would look at the name that comes first. It would be ethyl, and it would still fall under the number 3 if we were to number the parent hydrocarbon. So 3, and then 4, 5, 6. So everything would stay exactly the same. But that's not the case for all compounds, so be really careful. But I just wanted to show that it's possible that you can get to the same answer using 2 different parent hydrocarbons. Okay, and our final main idea for this video for saturated hydrocarbons is that the properties of alkanes are related to the lengths of their carbon chains. So properties of alkanes are affected by structure. Properties for some straight chain alkanes are listed in figure 2.4. The trends in these properties can be explained by examining the structure of alkanes. The carbon-hydrogen bonds of alkanes are nonpolar. So the only forces of attraction between nonpolar molecules are weak intermolecular forces, which we refer to as London dispersion forces. I love that they're called London. And now the strength of London dispersion forces increases as the mass of a molecule increases. Okay, so let me write this down real fast here. Properties are affected by structure. And as the final sentence says, by structure. Molecular mass is directly proportional to the strength of London dispersion forces. And I would also like to note here that it says that carbon-hydrogen bonds of alkanes are nonpolar. However, so the reason they're not polar is because the electronegativities of carbon and hydrogen are not too different. But if it was an oxygen atom bonded to a carbon atom, to a hydrogen atom, or a nitrogen atom bonded to a hydrogen atom, the bonds would be polar, and that is because the electronegativities of oxygen and nitrogen differ a lot from hydrogen. And so there's a partial negative charge at the more electronegative element, so oxygen and nitrogen would have a partial negative charge, and hydrogen would have a partial positive charge, and that's what would make the bond polar. So the larger the difference in electronegativity, the more polar the bond is. We're going to come back to figure 2.4 in a second. So physical states. The physical states at which some alkanes exist at room temperature and atmospheric pressure are found in figure 2.4.
Alkanes that have the lowest molecular mass, those with 1 to 4 carbon atoms, are gases. Natural gas is a fossil fuel composed primarily of alkanes containing 1 to 4 carbon atoms. These alkanes are gases because they are very small molecules. Therefore, they have weak London dispersion forces between them and are not held together tightly. So, as a rule, a small mass means weak London dispersion forces, or intermolecular forces, meaning that atoms are not held together as tightly, so their atoms are farther apart from each other, and the substance itself is less dense. And as we learned from basic chemistry, the least dense form of matter is a gas. So that's why smaller compounds tend to be gases at room temperature. Larger alkanes are liquids because they have a greater mass, molecular mass. Gasoline and kerosene are examples, and they consist of liquid alkanes. Gasoline and kerosene. Stronger London dispersion forces hold these molecules close enough together to form liquids. So yeah, it all comes back to this cause and effect. Alkanes that have a very high molecular mass are solids. Here, solids, corresponding to a greater increase in London dispersion forces, meaning that atoms are held together more tightly, and so the substance is more dense, and so it's a solid. Paraffin wax contains solid alkanes that can be used in candles, as shown in figure 2.5. So going back to figure 2.4, we see that compounds that have 1 to 4 atoms, as identified by the text, they tend to be gases at room temperature. And then as the number of carbon atoms increases, the compounds become liquids and then solids at room temperature. The mass of hydrogen atoms is negligible because its molecular mass is 1.008 units, atomic units, whereas carbon is 12. And so as we go down, molecular mass increases, as well as the strength of the London dispersion forces. So strength of London dispersion forces, I'll abbreviate it as LDF. Yeah, and that's why, and they affect the state of matter at room temperature. Figure 2.5 shows us solid alkanes. Paraffin wax is used in candles, and it contains solid alkanes. Molecules of paraffin wax contains 26 to 30 carbon atoms. So they're solid. They're solids at room temperature. Now we'll look at boiling points. The boiling points of alkanes, also shown in figure 2.4, increase with molecular mass. And then this is again tied to London dispersion forces, because as London dispersion forces increase, more energy is required to pull the molecules apart. And then this all goes back to the fact that London dispersion forces are stronger when molecular mass is greater. It also affects the boiling point. This property is used in the separation of petroleum, which is a major source of alkanes. So let's go back to this table and add that the boiling point is also increasing. back to petroleum. Petroleum is a complex mixture of different hydrocarbons that varies greatly in composition. The hydrocarbon molecules in petroleum contain from 1 to more than 50 carbon atoms. This range allows the separation of petroleum into different portions that have different boiling point ranges as shown in figure 2.6. So in fractional distillation, it's a process that separates the different hydrocarbons. Components of a mixture are separated on the basis of boiling point by condensation of vapor in a fractionating column. Figure 2.7 shows an example of refinery towers in which this process takes place. During its fractional distillation, petroleum is heated to 370 degrees, and nearly all components of the petroleum are vaporized at this temperature. As the vapors rise in the fractionating column or tower, they are gradually cooled. Alkanes that have higher boiling points have higher condensation temperatures, so they condense for collection lower in the tower. For example, lubricating oil has a higher condensation temperature than gasoline. So lubricating oils, for that reason, are collected lower in the fractionating tower. Now, the reason this whole petroleum thing is brought up is because petroleum and natural gas are essentially saturated hydrocarbons, and as we said, it's a major source of hydrocarbons in the first place. So yeah, again, just to recap, as London dispersion forces increase, more energy is required to pull the molecules apart. So that's why the boiling point also increases as the mass increases. Now, figure 2.7 shows these petroleum refinery towers where this process of fractional distillation takes place. And figure 2.6 kind of helps understand how this process occurs. Let's start with the fact that petroleum is a complex mixture of different hydrocarbons. And different hydrocarbons, they vary in composition, which means that they will all have a different molecular mass, and so they'll have a different strength of London dispersion forces, and consequently a different boiling point. So it's a mixture of all kinds of hydrocarbons. And so when this mixture of different hydrocarbons is boiled, the individual fractions of petroleum will boil at different times, at different temperatures. So they will boil in gasoline will boil faster than kerosene, and then kerosene will boil faster than diesel or middle distillate. And so lubricating oil, for instance, will boil the last. The boiling process will be stopped at 370 degrees when almost the whole mixture has been turned into vapor. So now there's only vapor in this tower. And then as the vapor is gradually cooled, the condensation process will also happen at different times for each individual fraction. So condensation will go in the opposite direction. Because lubricating oil, for example, has the highest boiling point, it has the highest condensation point, condensation temperature. So lubricating oil will condense first, even though it boiled last. So because it boiled last, it will condense first. And then as it condenses, only lubricating oil condenses until a certain temperature. It will be collected in the on the bottom, and then diesel will start condensing. And then there will be a stop, and diesel will be collected a little above. So, and then like this whole thing becomes a layered milkshakes. Like, have you seen those milkshakes with different layers? It's the same with petroleum, as they all before they boiled, it was a smush of things, and then it all evaporated, and when it starts condensing, turning from gas into liquid, the the most dense part will go to the bottom. So lubricating oil, and then diesel, and then kerosene, and then gasoline. Because gasoline was the last to turn back into liquid, to condense. It will be at the top, and then lubricating oil will be at the bottom because it was the first to turn back into liquid from gas. So I hope this makes some sense. See you in part 2 of this video.